Okay, no, those are the problems, and people are having the instinct to do the right thing with these problems, to change the exponential form to logarithmic, or to change the logarithmic form to exponential. What I'm not seeing is that people know the rule. Okay. Now, everybody had the homework, and the people that did the homework did well. But nobody remembers the rule, which tells me that you're doing the homework with the rules sitting right in front of you and looking at the rules every time you do a problem. Either that, or you just don't have a great memory, and you know, that's okay. You remember the gist of it. Okay, everybody remembers the gist of it, and that's good. That tells me that everybody is capable of really knowing what these rules are, and hopefully knowing why the rules are what they are. Because that really helps you remember the rules. When you get a test, you know, you don't gotta have those rules in the test. Gotta know the rules. Okay, so the way I write the rules, fairly similar to the way the book writes the rules, except they use a B, and but in what I consider to be not the best idea, because B should be the base. But let's say you have B to the A equals C. So I'm using A, B, and C. So your book, I don't remember what your book uses for the base here, but this is the base, and I really want it to be represented by the letter B for base. Okay, so we have B to the A equals C is equivalent to. There's the sign, that means equivalent to, means it. If it satisfies this, it satisfies this. This would be log base B. And if you remember that B is the base, then it's a little easier to remember this part of the rule. Then it's just a matter of where does A go and where does C go. And one way to think of this is if you're trying to solve for A, you can't do it when A is your exponent. Okay, so the reason you change this to logarithmic form is so you get something that's equal to A. So A goes from the exponent to right here where you want it. You want to solve, and that leaves only one place for C. It's right here. Okay. So log base C, log base B of C equals A. All right, well, we have 4 to the x minus 3 equals 2. Using this rule, we identify A, B, and C. B is your base, that's 4, that's the easiest thing to do. A is your exponent, that's x minus 3, and we want to get that out of the exponent because we want to solve for x. So we're going to use this. Okay, so again, everybody has the instinct to do this. Put the details down and you'll be fine. So this comes down to log base B. Well, base 4 in this case. Again, 4 to your base, it goes here. Okay. It better equal your x minus 3. Because the goal is to get the x minus 3 out here, and you remember the rule, and you see that, yeah, that's right. And 64 has got to go. Okay. Well, log base 4 of 64. 64 turns out to be a power of 4. So I can actually make a table at 4 to the x. Okay, but there's the first 4 powers of 4. So I made it easy on you. You don't have to go to your calculator to do this. Although you could go to your calculator. Okay. log base 4 of 64 has to be 3. Why? Because 4 to the third is 64. Here's your table for 4 to the x. The log base 4 table. Which column? So when you have a problem that looks like this, it takes only seconds to do this. If you know the powers of your number. Now, if it was 7 to the x minus 3 equals 243, 343, you wouldn't necessarily know that 343 is a power of 7. Okay. To the power of 7. But for smaller numbers, you can often do this. Anyhow, whether you do this or not, you get 3 equals x minus 3. You might have an intermediate step. Might have to go to this step to get this. You might not see this, and that's okay. Saves you a little time if you do. It gives you more insight. Okay, well, where are we? We've converted the equation to exponential form, or to logarithmic form. We've taken care of the log, which is just log the given base, the given number. And now we have 3 equals x minus 3. Add 3 to both sides. You get x equals 6. Then we can check by plugging back into the equation. What's 4 to this 6 minus 3? X is 6. That gives you 4 to the third. 6 minus 3 is 4 to the third power, yep, is equal to 64. Here's a full circle. Okay, log base 2 of 2x plus 5 equals 3. Well, again, the x that you're trying to solve for is inside of that log function, and you've got to get it out of there. So you're going to convert this to exponential notation. Your base is going to be 2. And you hope that your exponent is 3, so you can put the 2x plus 5 over here. And then you check that out with the rule to make sure. And you find 2x plus 5 equals 8. You do the routine steps. You end up with x equals 3/2. Now you check that out. If x equals 3/2, you plug it in. 2 times 3/2 is 3. 3 plus 5 is 8. So log base 2 of 8 equals 3. So if you have a table, imagine the table of your 2 to the x function, and then reverse it. You can see that. You can see that it's so 2 to the third power is 8. Or you just say, well, this to this power better equal this. You get used to it. But you got to do a lot of problems without looking at video and the solution, okay? And there are always enough problems where you don't have a video. You shouldn't have to go back to videos you've already digested. Although if you do have to, yeah, go ahead, but whatever it takes, make sure you internalize these rules, okay? Okay, so again, everybody's doing well in this. Again, you have the right instance, yep, the details down. Okay, so look here now, we got two. Log base 2 of x plus 4 equals 4. Now, there's actually two choices here. You could divide both sides by 2. And then you have this form. You don't have this form right now because you have had 2 out in front of the log. There's no number out in front of the log here. But if you were to divide by 2, that would work fine. And I'm going to do it differently. I'm going to say using the rule of logarithms that we saw last time. Okay. A times log x equals log of x set to the a. And those are rules that you just got to know. And the assignment, we actually use those rules is just do, I think, okay. So I don't necessarily expect you to remember those rules, but if you were in class or watching videos and took notes, okay, you would know. Or at least you'd be familiar with it. Most of you think of it. If not, it's not a difficult rule. Those rules are not all that difficult. With practice, they kind of become natural. Take practice. Okay, so anyhow, you have this, and you convert this using this. You know, your B is 2, so that's your base. Your A here is your x plus 4 squared. And your C is, where is it? 4. Okay, well, that gives you x plus 4 squared equals 16. And I guess we'll put that up here. X plus 4 squared equals 16. We're going to move this over a little. Okay, x plus 4 squared equals 16. So that x plus 4 is plus or minus the square root of 16. So x plus 4 would either equal the positive square root of 16, 4, or negative square root of 16, which is negative 4. Solution here is x equals 0. Solution here is x equals negative 8. Then we can check it out with the original equation. If x equals 0, we have log base 2 of 4. There should be 2. Multiply that by 2, you get 4. That works. Plug in negative 8, and you want to do this. You want to write this out. We plug in negative 8. Negative 8 plus 4 is negative 4. And all of a sudden, we realize we got a big problem. You can't do a log of a negative. Just make a graph if you need to. Thank you. Okay, so and if you know 2 times 2 equals 4, that text I don't really bother talking that one through. This is very straightforward. Sadly, X minus 4 is going to be rejected. It's going to feel terrible. Okay? The negative numbers can't handle rejection. Well, X minus 4 gets rejected. Why? Because actually, I should write that as negative 4 plus 4. X is negative 4. We're going to get a 0. 0 is not in the domain. Not in the domain of the log base 2 function. So at this point, sorry, X is negative 8 there. Yeah, 0 is not in the domain, but it's important is that negative 4 is even more so not in the domain, not even close. Okay. So at that point, cross out our negative 8. This is our mistake. Well, I think you all are pretty well prepared to do a few more problems. So let's just pose a few and see how you do with them. All right, again. There's a good things going on with the detail. They're still tending to slip out through little holes in the side of the tin or whatever. Okay. So let's look at this. Okay, so we've got this. And well, that's a log of A plus a log of B, isn't it? We have a log of one thing added to a log of another thing. If we have a log of A plus a log of B, that's a log of A times B. So we want to write this down as log base 2. Of the quantity X plus 4 times X minus 3. And that equals 3. Now, there's a temptation to want to apply one of these equivalences to this equation, but you can't do it because you have a log, one log plus another log. There are no two logs there. There's just one log. So we've got to use this rule to write this in terms of one log. Okay, that's why we use this rule. So now we can convert the form using this equivalence. We're going to get 2 to the 3rd again. I'm going to cooperate. Very clear. 3, 2 to the 3rd. And of course, I'm going to operate somewhere. 2 to the third equals x plus 4 times x minus 3. So h equals x plus 4 times x minus 3. And what kind of equation is this? Well, from what we did a few weeks ago, we should recognize that immediately as a quadratic equation. That's algebra 2. Okay. But we went over that. If we expand this using the distributive law, we're going to get something that's recognizable as a quadratic expression on this side. And of course, we should hopefully recognize that at this point, because you're not going to be able to solve this unless you recognize that. All right, well, and I've seen some of you, expanding this sometimes at the wrong time, but or sometimes having skipped a step, which I think is really a bad idea right now. Still, right instincts just fill in the details, right? So let's solve this equation. And I don't spend a lot of time with it, need to review this. Okay. Well, right, you got to do this using distributive law. I've done the details of the distributive law so many times. And I'm not going to do it again, not because I don't want to, because we just can't take the time to do this, okay? And the distributive law keeps escaping people. We need more drill in the distributive law, and I'm working on getting some more drill into this course as soon as I know how to do a drill that you can repeat. Okay, and I've got to ask somebody about things. Ask ChatGPT, how do you do it? Because I don't have time to digest the whole programming language behind open math. I know what we can do. I do it sometimes. So I got asked. Anyhow, we got this. Right. We're gonna do some drill stuff. Hopefully I'll get that up for next week. It won't take long to do. But right now, all I see is we got a set of problems with new ones. I'm not even sure. Yeah, I know. Okay, well, see that kind of direction. Need some drill on solving equations. Because people are insecure about that. We'll try to get that for you sometime to use some time on it. Okay, so we have this equation. This is a quadratic equation. We put this into the form x squared plus x minus 20 equals 0, and use the quadratic formula or factor. Turns out, I think this one could factor. This could factor is x plus 5 times x minus 4 equals 0. I was going to say probably doesn't factor because probably does. I didn't choose the number so it would, but we just left out that factor so that x equals -5 or x equals 4. We have to reject it's like we've got to reject both of these solutions. Because if x is -5, both of these are negative, right? Actually, we don't have to reject both. We're going to have to reject 5. Okay. If x equals 4, then we get something that makes sense. Okay. Right, so kind of small with that. X minus 5 is rejected because log 2 of x plus 4 would be log 2 of negative 5 plus 4, which is log 2 of negative 1, and negative 1's not the negative. So we got to cross this out. X equals 4 is okay. If we plug in x equals 4, this is what we get. We can easily verify that. That's log 2 of 8 plus log 2 of 1 equals 3. 8 is 2 to the third power, so log 2 of 8 is 3. 1 is the 0 power of 2, so that's 0. 3 plus 0 equals 0. It works. Now, again, another thing, if you're not checking your solutions, then you're missing a whole lot. Okay? Not doing all the checks, you're missing the basic ideas and the full opportunity to understand what you're doing. Okay? But certainly on your homework, you should check every solution. Okay, well, see what you do with this. It's similar, but it's different. And it also reviews an important aspect of problem solving, of equation solving. Okay, for this problem, which had 4 here, and everybody solved it with 4. But when I wrote it down, I accidentally wrote 3. So when you solve it with 4, I'm solving with 3. It's easy to solve if you know how to solve it. Okay, so what you see here is you have an instance of what? Which of these rules applies? The first one, second one, or the third one? It's the third one because you have log of A minus log of B. This is a log of A minus log of B. Okay? And that equals a log of A divided by B. Okay. Most of you got that. If you didn't, make sure you know how to look at this. But of course, the homework that you have, I think you're going to do okay. Okay, so here we have it again. Here's the equation. And then I've just rewritten it. The log base 2 of x plus 5 over x minus 3, which is the difference of 2 logs, gives you the log of the quotient. We then convert it. It's 2 raised to the third power equals x plus 5 over x minus 3. And then you have x plus 5 over x minus 3 equals 8. Now there's a heuristic rule that I emphasized earlier in the semester for solving equations. And does anybody remember what that heuristic is? Okay, now I've stressed this a number of times because we've used it a number of times, but it still isn't triggering. Okay. I knew where. Okay. Yeah. Unfortunately, we have somebody said something and we can't do that. Okay. And the person's already forgiven. I hope I remember to add that on. Okay. And I really hate the fact that we can't just have a two-way conversation and do videos. On the other hand, we don't want somebody saying something really embarrassing and having that out there. Because in a math class, it's really easy to say embarrassing things. I do it all the time. See, I approve it. I'm the one that posts the video, so I can't sue myself. I did, I give a lot of money. No, I don't have that. No. Well, anyhow. Okay, we have this equation. And the thing that needs to trigger is you have a denominator, you multiply both sides by the denominator. And you also try to remember to also write down, well, we're excluding values to make the denominator zero. Big thing is multiply by that delimitable denominator. Okay. And you really need to lock that in. I don't know. So, I think in the last class, there's something I needed to remember. I didn't remember my tattoo needle, or I tattooed backwards in my forehead or something. Okay. If I had a tattoo needle, I'd loan it to you. You wouldn't do that. But you get the idea. It's important. So I'm going to pause for a second and let you write this down someplace, so it comes to your attention, and then write it down in an even more important place, so you remember to do it, because it's going to cost you points, probably letter grades worth on the exam if you don't. Okay, so they're multiplied by the common denominator. Then we get this, which is really an easy equation. X plus 5 will then be 8x minus 24. And we subtract 8x from both sides, we're going to get negative 7x. Got 5 from both sides, we get negative 29. So the x is 29 over 7. Then we plug this back in. I'll be able to do the fractions. 29, 35 is 64 on the numerator. It'll be 64 sevens. And the denominator would be 8 sevens. Gives 56 sevens, which would give us log 2 of 8. And that does equal 3. We should be able to do those fractions. Okay. So you should be able to check this doing the fractions, which reinforces the type of arithmetic you have to be able to do, which also contributes to understanding how to manipulate rational functions. Okay. Very, very important. You know, make test to get over rational functions. And it's going to figure significantly on the final. Okay, now there are 2 things we need to know in order to solve problems, to solve equations. Okay. How to convert from exponential to logarithmic, or logarithmic to exponential form, which you will do fine with if you practice properly. Okay. And how much practice you need to realize this, I can't tell you. Like I said, I'll get you some real problems. Okay. Then here, we have 3 rules for logs, which are reciprocal in a sense, or inverses of the rules for exponents. And you've got to know the rules for exponents. So I'm going to leave it to you to make sure you know those rules. Okay. You're going to need to use them there to solve the equation we've already used 2 times. All right, so there's that many. Okay. I've got a little bit, all right. Two that are most commonly confused are if you take x to the a times x to the b, it's x to the a plus b. You notice that multiplication becomes an addition, right? I mean, the multiplication doesn't really become an addition. You got something that expresses a multiple here, and you got an addition to the exponents here. Here, you have a power of a power. An exponent applied to something's already got an exponent. Raising power to a power gives you the product of the powers. Okay, now here you have a multiplication associated with an addition. Isn't that what you have here? It kind of goes the other way, and I'm not going to belabor that because you just make figure it out. And here we have a multiplication. It moves over to an exponent. Okay. So you can see how these two rules are kind of related to these. Now there are more rules for exponents. Any number to 0 powers 1 and all that. You have to know them all. And you should understand them and understand why they work. That way, it's much easier to remember them. I never memorized the laws of exponents. I was too dumb to memorize them. I just took an example. If we do x to the third times x to the second, well, that's 3 x's being multiplied together, 2 x's, that's 5 of them. So we add the 3 and the 2. Okay. If it's x to the third to the second power, then we have x to the third times x to the third. That's a string of 3 x's and another string of 3 x's. That gives you a string of 6 x's, which is x times 3. You know, 2 and 3. You can check out these rules. So if you think you have the rule right, but you're not sure, just test the rule out to the side. Let the exponents be 2 and 3. And see if what you think is consistent with what it has to be. All right. And so it's actually, I found that much easier than memorizing. It's just like the Fahrenheit to Celsius conversion. I remember my outstanding high school physics instructor, chemistry physics instructor said, only a fool tries to memorize those conversions. You learn to reason it out. Because it's kind of hard to memorize. There are many other cases where things that are confusing to memorize are easy to understand, but everybody wants to memorize them or nothing. Okay, this is an instance of that. These rules. Okay. And we talked about this last time, so we talked about the validity of a logarithmic function. But let's look real quickly. Log to the base 2 log. Let's say we got y equals log base 2 x minus 4 quantity squared. What's the graph look like? I'll do plus 2. Okay, first of all, we're going to transform the log base 2 graph. But first, I'm gonna rewrite this as y equals 2 log base 2 of x minus 4 squared. Now we transform log 2 graph. The vertical stretch factor is 2. We have 2 times the log base 2 of something. You have a horizontal shift of +4 because the log base 2 of x functions has first been doubled. You got the 2 out in front, that gives us a vertical stretch 2. And then x has been replaced by x minus 4. And I'm gonna square up that. Okay. X has been replaced by x minus 4. Then a vertical shift. +2. What's that look like? Well, you construct your log base 2 graph. And I'm doing this quickly. And I've done this a number of times. But to do it, you take your 2 to the x graph table and go to columns, switch the column, and you get your log base 2 graph. So here it is. Now here's -2. And here's 2. Here's 2, here's 4, and the rest of the numbers are known implicitly. So we vertically stretch it by a factor of 2. How do we do that? Take every y value and double it. Again, we've done this a number of times. Now, I'm not going to explain the details since we're just about out of time. And here you get the graph of y equals 2 log 2 of x. Then you shift every point 4 units to the right. Well, fortunately, we're out of time, so I don't have time to embarrass myself by trying to draw the rest of this graph off the board over there. Okay? But yeah, you're gonna take this point, move it over 4 units. You're gonna take this point, move it over 4 units. And you're gonna do all that. We've done it before. Look at what we did last time. And then we're gonna raise every point off 2 units. Okay? So there's the process. Homework is going to ask you to look at some graphs and try to identify how it's been stretched, shifted, and so forth. And the videos will help you see how to do that. When I test you on this, I'll ask you to show me the transformations, just like I do on any other function. And what we do with the transformations is no different. Shift horizontal arrows, shift use vertical arrows, double things, we use double arrows, and so forth.